I'm the a co-founder of a dental AI startup, up and coming, but really fortified by its partnerships, which I'll go over in a few slides. But basically, we are a dental AI startup that looks to solve problems. So let me first also want to get through a few thank yous real quick, but also thank you for you guys for taking some time out of your Wednesday to listen to me. I do want to add a few disclaimers real quick. Is just that as you probably noticed by the title, that I don't have a PhD, and so I'm not the most kind of qualified to give an in-depth technical and overview of this, but I've done my best. The co-founder, CTO of Dentuit Imaging is actually John Winder. He does have a PhD, and he was kind enough to at least vet and screen through the slides and make sure that there's no blatant mistakes or errors or anything like that. So you can at least trust me on that. So the goal really, so there's a few motivations why I sort of agreed to sort of, oh, by the way, I wouldn't be insulted if you guys dropped off or somebody dropped off around 4:33, because I would be remiss to not acknowledge the fact that there's a pretty historic space launch today, the first ever commercial partnership, in this case SpaceX and NASA around 4:33 Florida. They're launching.
Maybe I can stream that in a window separately.
Yeah. Seth won't be happy about you guys dropping off, but I won't mind. That's fine.
Yeah, go for it, Dan.
All right. Okay. So some of the motivations, of course, is it forces me, as I do have a day job for now, anyways. In addition to the startup, as a data engineer for a federal government contractor, and as some of you know, when you have a day job, it's hard to kind of keep up with the quickly kind of rapidly evolving technology like AI. But so it forces me to kind of refresh, learn, and be able to practice, clear communication, which again, hopefully I can do some of that by the end of the presentation. Really also to be able to kind of give you a glimpse, an overview of basically what is deep learning, and then how does that get applied to something like medical imaging, which is similar to then what we see in other healthcare related AI use cases. But this is specifically going to be on deep learning applied to medical imaging, and hopefully throughout this overview, very much an overview that you guys can go ahead and Google certain things on your own and self-learn on the details that may interest you. Finally, the last motivation, of course, is to put in a little plug for our startup, Dentuit Imaging, with our, again, fortified by our partners, and I'll go over that, including the University of Maryland, Baltimore. Some of the attendees from the School of Dentistry are here, and I will acknowledge them in a few slides. But so what is Dentuit Imaging? What do we provide? What are we trying to do? Well, I think a good startup always looks at the problem first, always tries to solve a problem that actually exists in this world. And in this case, it happens to be in the dental kind of a workflow. We see oftentimes in a typical practice, you'll be with one dentist. You're not going to have a group of dental experts, providing their, let's say, insight or expertise while analyzing and examining whether an X-ray right before then they reconcile their findings from the X-ray over to what they see manually in the patient's mouth. And I do believe that dentists are kind of unique in the sense that they're expected to be a little bit of everything. When you watch their workflow and what they're expected to do, they're actually expected to be a little bit of a radiologist and then go over and then really do the manual work with their hands, and hopefully they're competent in all those areas. But the fact of the matter is, dentists are actually human beings, and much like doctors as well. And so with that said, errors are made. And in this case with X-ray examination, not germane to dentistry, really in medical radiography as well, is that the inter-examiner agreement, the consensus that on one X-ray image is quite low, is shockingly low. Maybe we shouldn't be surprised that it's low, but it's low, and it can get concerning, and it gets kind of evolved into complaints with dental situations where you wonder, oh, is this dentist trying to nickel and dime me, et cetera, et cetera, et cetera. So what if, and then the current digital solutions that try to resolve this really kind of hit a ceiling at the point of image processing, but nothing beyond that. With amazing filters is what they say to give you really crystal clear images if you buy this really expensive sensor, and be able to help you um, 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 kind of find something in the X-ray. But what if we can kind of provide that kind of oversight that you have with a panel of experts within a millisecond, within a few seconds, through a simple graphical annotation that does not disrupt your workflow. It does it in a seamless way. And that is exactly what we're trying to build. It's basically, and this is, no real different than what you'll see in the medical field as well. Along what you see with Google AI and DeepMind, and I'll go over that a little bit in the later slides, is that you're not going to see a substantial decrease in time in terms of, well, am I going to, be able to, save X amount of time if I use your technology, but rather it gives you the ability to have and provide this kind of oversight that you would only typically see, let's say, in a dental school clinic, which would take a lot more time, a lot more visits, and a lot more kind of, yeah, a lot more time that we can then shrink that into a regular visit that you see at a regular dentist. And to be able to do that in a graphical annotation with a graphical annotation and do that in a reliable, consistent, and for us, we're building the world's most robust caries detection system to start. And I say that very, very confidently. And I'm excited to, and this picture is there really just to demonstrate that we want the dentists to really focus on what they're really good, what they're really trained at, and what they're really specialized at is that, rather than trying to spend time examining and looking for patterns in an X-ray. And I'm really happy to kind of use this platform finally to kind of announce that, we just recently, after years work of partnerships with, in the applications, with the folks at, the School of Dentistry at Maryland, through the partnership with that, we got the SDTR. We've been awarded the phase 1 grant to really kind of provide us this opportunity to kind of do R&D with clinical partnerships. And I want to emphasize, and I really use this slide not to really boast about this, but one, to acknowledge really the partners that are here in attendance. And so Dr. Jeffrey Price, Dr. Vineet Dar, and Dr. Vandana Kumar, they're all directors of oral radiology, pediatrics, ortho, and oral radiology. They're all, they didn't have to, take a chance on someone like Dentuit Imaging, but they did from the very beginning, from day one. They were really excited about our vision and what we can possibly do with, let's say, deep learning. And so I'll get into that. So what I just want to emphasize real quick before I then go into the actual presentation is that if you guys are kind of looking into, building a solution, or hopefully a solution, right, to a problem that exists with AI, that you're not just throwing AI at the wall and hoping that something sticks because AI. Rather, it is this notion of interdisciplinary collaboration that you'll start seeing more and more. But we're very proud to kind of have been granted that opportunity through the University of Maryland School of Dentistry, as well as the NSF endorsement and their R&D grant, and taking a chance on us. It is only through such collaboration and open-mindedness that you will get, capable and clinically performant technology. And I will go over that again in later slides. Okay, so why medical imaging? What's the big deal? Why is it done? And what's the point? Obviously, there's many ways to capture information, whether it's text-based, but in respect to images, physicians or dentists, they take images from the body to get meaningful information about the patient so that they can then make an informed decision, if you will. And that breaks down to basically three things, which is pretty kind of familiar to us. For one is medical imaging allows the doctor to screen for possible health conditions before symptoms appear, diagnose the likely cause of existing symptoms, and monitor health conditions that have been diagnosed, and allow better treatments from that. I emphasize the second point, diagnose, because I will make very clear that I do not believe AI is at a point, far from it, that will allow for any sort of diagnosis. It is all about allowing the physician or the dentist to make the best diagnosis with a technology like ours as an assisting kind of opportunity through detection of things in the X-ray or information about the patient, et cetera, et cetera. But we are not claiming whatsoever that we can diagnose this because we understand that that's a much more complex situation. Okay, so there's different types of medical imaging. These three here, we should all be somewhat familiar with, are examples of radiation based imaging. And you see sort of the difference here. And each type of medical imaging module kind of is used for a very specific purpose. They all have their respective pros and cons. There's not one imaging that's better than the other. Whether depending on the density of the organ that you're kind of imaging, there's various factors beyond the scope of this presentation. These three here, MRI, ultrasound, and endoscopy, are just some of the non-radiographic imaging that also exists, and there's many more. So pretty much, why am I even talking about these devices and these devices that kind of produce these images? And I'll get back to that in a later slide. But first, let's break it down a little bit. I was told that rather than trying to assume so many things, I want to see if I can, in the most simplest and clearest way, explain certain things that allow for deep learning to even take place. And so it all starts really from what one would kind of look at as a neural network. And so neural networks are nothing more than a set of algorithms modeled loosely, of course, after the human brain, designed to recognize patterns, computations that allow to recognize patterns. What does that mean? They interpret sensory data through a kind of machine perception labeling, from labeled images or any kind of knowledge that is kind of given to the algorithm as training. The patterns they recognize are numerical, however, and I do want to emphasize that, contained in vectors. And so this is kind of, if you see the red kind of array there right before the cat yes or no, that's a vector. And what they're basically trying to represent here is that an image is nothing more than a matrix, a table of numbers. These numbers relate to pixels. So if you're talking about black and white images, it will be between any number between 0 and 1, talking about RGB or color, talking about numbers beyond that. And so these are numbers that then gets computed in various ways while it tries to understand and classify, in this case, whether that image is a cat or not. And so I'll go into that a little bit later, the differences between the various tasks that these neural networks can do based on the neural network, etc. And so these neural networks are kind of composed, let's go just one more level down without getting too complicated, is composed of what? These are composed of algorithms, and algorithms are nothing more. So algorithms basically as a node. And so as one node, this is one node right here at the very top, combines input basically with a set of coefficients of what they call weights that gets kind of adjusted, and that's the learning process. And then the input and the activation function. I'm not going to go too much into the activation function, but the point I want to make here is that this represents one node, and then a node layer is then created with a bunch of nodes, right? More than one nodes. And there's three kinds of layers that make up. I'm not going to say all neural like a convolutional, for example, or your typical neural network will have an input layer, a hidden layer, for and an output layer. And I will emphasize hidden layer because the hidden layers are what kind of define deep learning, if you will, or allow deep learning to be defined in contrast to something like machine learning. And so what do you mean by that? Well, let me just do a quick history lesson real quick. And so around the 1950s, neural networks that I kind of basically briefly kind of introduced here, what were introduced loosely modeled after kind of neurons, like I said, in a biological brain. But it suffered in terms of performance and accuracy due to a lack of computing power and absence of sufficient data. And you will see that as a recurring theme over and over. And that is why I kind of sort of emphasized the advances in medical imaging earlier with the devices and that becoming more and more advanced, sure, kind of providing more and more opportunities to have high quality images, store images in large quantities and such. And so with the advance of such kind of medical imaging, it also gives way to opportunities to then use that information in some meaningful and hopefully useful ways. And so in the 1980s is around actually when, the first kind of machine learning algorithms were introduced. And I'll go into that, in terms of how that differs from deep learning. But these, basic machine learning algorithms were crafted by people. No joke. These feature kind of extraction, let's say edge detection or what have you. These are all various algorithms that was very time consuming and labor intensive in terms of having these computer scientists just with, in tandem with the medical expert, the domain kind of expertise to handcraft these algorithms. And so it would really fall on its face when an imaging from another patient was then where that algorithm was applied to that image, because it just could not adapt to a slightly different image, because guess what, everyone is slightly different, and the imaging also will be different from patient to patient. Starting around early 2000s, you start to see something called computer aided detection, which is not what, for example, Dentuit imaging is necessarily building. It was created based on the machine learning algorithms that I referenced, from the 1980s. However, it really suffered from kind of producing more false positives than the physicians, and pretty much led to just greater assessment time and additional biopsies, which is the exact opposite we want to achieve with, let's say, deep learning based imaging. With some kind of computer aided, we want to use computers to be able to have less assessment time with less biopsies, but retain, if not more, have a high quality of diagnosis that come from that. So today, right, deep neural networks exist. So what is the difference? Like I said here, there's an input, and then with the machine learning from the 1980s, these feature extraction algorithms literally were handcrafted by people. And then they were used to kind of, within some kind of stacking of layers to classify whether, let's say, in terms of a classical classification task, whether that's a car or not. With deep learning, the idea is that the features are learned on its own in this one kind of tandem without any human intervention, handcrafting a specific kind of algorithm for a specific feature, for a specific diagnose, for a specific kind of, let's say, tumor that we're kind of trying to detect. Uh, it learns on its own rather than having somebody kind of code up an algorithm for that. And so what is really deep learning and the deep learning neural network here? Basically what you'll see online is basically what it is, right? It's by depth. You have more, layers, hidden layers specifically, in between the input and output layer. Still the three layers, right? The three types, the input, hidden, and output, but it's deeper, hence, deep learning neural network. However, I found this, and that's why I put a link there, and I'll share the PDF of these slides if you guys want, but I really liked this definition here, and so I'll read it here. So deep learning is a subtype of representation learning, which aims to describe complex data representations using simpler, hierarchized structures defined from a set of specific features. And so that kind of, in my mind, captures how deep learning works. And we'll go into that a little bit without me hopefully confusing you guys. But basically, let's look at kind of an example, an example of a deep learning neural network. And in this case, the most common one, especially for imaging, is the convolutional neural network. I make a point here that that's not the only kind of neural network that exists. It just happens to be that convolutional neural networks are very good at imaging-based tasks. What makes it a convolution? Well, I'll get into that real quick through the two main parts. But I do want to also emphasize, and I'll get to that again in another slide, hopefully, is that, even convolutional neural networks has its limitations when it comes to various imaging tasks. It's very good at, let's say, classifying certain things. However, when it tries to do more complex tasks than that, we have to look at other neural networks, if you will. And I'll go over that very briefly. But a convolutional neural, or the most kind of, the common one that you can think about, is that it breaks down between a convolution pooling mechanism right here that breaks up the image into features and basically analyzes them. And then in this case, it typically between the convolution and pooling, it's one after another, and then it kind of repeats itself. So the convolution, pooling, and then it vectorizes, like I said, remember, into an array of numbers that basically then allows it to reach the output and basically kind of determine whether this is the kind of with certain probability, what the object is, if it's a classification problem or a task. The second component of the CNNs, without confusing, is a fully connected layer. In this case, fully connected because it's typically related to classification tasks that takes the output of convolution pooling, so it reaches all the way from one end to the other, and predicts the best label to describe the image. The predicting the best label to describe the image is what I'm talking about, is classification. However, the point, that without confusing you, is that there's other things that a computer vision algorithm can do beyond just classifying an image, right? And in medical imaging, it's, we need to have a lot more than just classifying certain images as a certain label. And I'll get into that real quickly. So what do I mean by convolution pooling? Basically, without getting into the math, these are pixels, right? If you want to think of it as a matrix of pixels, it takes, an algorithm takes the pixels and essentially does a convolution, element-wise multiplication and an addition. But basically, it does a convolution at the very top, and then the pooling is then taking the various nodes and the layers and sums them, and then does it all over again. And so this yellow thing would then be one of the red, and then it becomes an input to the next layer, and it does the same thing. The convolution pooling is a typical, I guess, way to kind of think of convolutional neural networks. And ultimately, it's based on all the kind of previous aggregates of the convolutions and the pooling to kind of reach a certain kind of understanding of various features that's been extracted and hopefully represent some hidden features in the images. And that's the whole benefit of deep learning, is this idea that we can find hidden representations that we just otherwise would not be able to just, intuitively kind of see from our very own eyes and our brain. So there's neural networks, and then there's the neural network architecture, right? And so, for example, a CNN is one kind of neural network architecture. And it just refers to the arrangement of neurons into layers and the connection patterns between layers, activation functions, and learning methods. It's basically the shape of a particular neural network, right? And so that if you see that, in terms of architecture online, that's basically what it is. And so the neural network model and then its architecture of a neural network determines then ultimately how a network transforms its input into an output being some kind of a prediction of whatever it may be. So some examples that are typically used in the realms of medical imaging, I'll just touch on. I don't want to go too deep into it, partially because I don't even know what some of these do, to be quite frank. But I believe, my understanding is that the ResNet here, the highlighted ones in the UNet, are particularly kind of used for various reasons, and I'll try to explain that in the next few slides, for the purposes of imaging in the medical space. And so, real quickly, this is an example, a non-medical imaging example of the various tasks that a computer vision algorithm can do with deep learning. First, like what I talked about at length, is image classification. That is nothing more than kind of associating one image that you see to a label. So this is a chair image. That's all it is. And image classification and localization then starts to look into where that chair is in respect to that image. But it's only one object. When we talk about multiple objects, we're talking about relativity, right? The relative spatial distance, let's say, between the trash bin and the chair. And we detect that this is a trash bin because it's on the floor, it's blue, blah, 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 versus, this is also a chair. That's object detection. It's just more than one things that you're looking to identify. And then this is the image segmentation, which I believe is the most kind of promising kind of task that can be utilized in various ways, but also the most kind of complex. But the most useful in terms of information that medical experts want to get from these images is a shape. You not only do you kind of understand that this is a chair and this is a bin, but you also understand, wow, this chair is shaped this way, etc., and it's on the left versus this bin on the right, and it looks like this. Because we're talking about tumor detection of cancer, you need to know that, right? So I think this is I represent this because it kind of nicely transitions from what I just talked about to basically how that applies, just as as an example, kind of how that gets applied in a medical imaging thing. So it goes from, it's not an order per se, I think, but it's just examples include the organ segmentation here, lesion detection, lesion segmentation and classification, monitoring, prediction. And so I do want to explain a little bit of each, if you don't mind. So I'm opening up the notes here. So the very top, the image pre-processing, it refers to the techniques applied either on the raw signals or on reconstructed images. I'm not going to go over image reconstruction. It's a bit yeah. So for example, deep learning methods have been used for image reconstruction from sparse MRI data. So that's one of many ways that I'll kind of talk about a little bit is how to deal with such limited data sets, which is very which is very germane to the medical field in terms of medical imaging, is that images are just very hard to come by, labeled images, if you will. And so detection is applied to medical imaging, refers to highlighting a specific subregion in an image, which is likely to contain a localized tissue, anomaly, tumor, what have you. And so you're able to kind of detect that this is a particular lesion. And this is exactly what we here at Dentuit are looking to do. We're starting with caries as the lesion, and we're looking to detect that this particular pattern that we detected from our algorithm based on our learning in this X-ray is a caries and not something else. Be it, let's say, a shadow of the X-ray image, which can often be confused between, from a human understanding point of view. Segmentation then refers to delineation or volume extraction of a lesion or organ based on image analysis. So it's pixel level, whether it's pixel intensity, texture, or edges. It's no longer just a general kind of, bounding box of an object, but rather, from the very shape into the coloring and then the filling in of that shape, pixel level. And I'll go into that a little bit. Classification, like I talked about, again, refers to categorization of a specific group or type to a lesion from one class to others. It can be binary, but it can be also multi-class as well. Binary can be as simple as you look at a COVID X-ray, right? And then you say, oh, this is severe. This is not severe. This is severe. This is not severe. That's classification. But what if we want to go beyond that, right? And that's the kind of things that you see in progress today in terms of the various computer vision efforts to kind of detect things like breast cancer, and especially lesions at early stages. And so you can't. I'll be remiss not really emphasize that, is that there's benefits of not only being comprehensive in finding certain things in an X-ray reliably every single time, but also detecting them at an early stage such that you can prevent more invasive, treatments or what have you. There's monitoring, like I talked about very early on, and then there's prediction, leveraging the specific features to anticipate, let's say, how this pathology will evolve over time. And so that starts to get the most complex. I think that's why it's all the way at the very end. And you're talking about adding, additional information to help make that prediction. But, you have to start somewhere. And again, like I said, we here at Dentuit, we want to, solve problems step by step, and hopefully keep it as simple as possible, starting with detection. We want to be very good, really good at detection before moving on to possibly other use cases in the oral or the dental field. So I'll move on to the next. So like I talked about earlier, the convolutional neural networks, they're really good at classification. That's what they're typically used for, classifying kind of, this is a normal, X-ray. This is an abnormal X-ray all the way to the right, right? However, it's not very good at segmentation. It's and so why do we care? How to also be really good at segmentation if you know that's if you it's really it's pretty obvious, right? Because in the biomedical cases, experts, radiologists requires that they need to be able to distinguish whether there is a disease, but also to localize the area of abnormality. This is an example on the left as a detection, right? Object detection. And then on the right is segmentation. And so this is where you need to, we start looking at, things like UNet and ResNet. And that's why I highlighted that earlier. They're not convolutional neural networks, nor are they even fully connected, right? Fully connection to me, in my mind, typically is related to classification. Just the way it works from one input to the very output. UNet and ResNet are kind of architected, still layers of nodes that we know from earlier slides, but arranged, right, in various ways, in specific ways to deal with certain things. Let's start with UNet without hopefully confusing even myself. Is that UNet was actually first realized as part of a better method in segmenting, doing segmentation tasks on biomedical images. And so I guess the easiest way to kind of think about it is that segmentation is pixel level, right? We need to understand, on a pixel level scale, what something is, or recognize that on a pixel level. And that's why labels, training images for tasks like segmentation are, literally not just a box, but you're coloring it in. You're coloring in a label because that's on a pixel level. But the UNet, how it's, and you can kind of imagine why it's called a UNet because of the shape. What it does is it converts the segmentation problem into actually a classification problem on a pixel level. So it classifies each pixel and associates that to a label. And so by doing that, without going too much into it, allows it to then be really good at segmentation as a whole. In a UNet, an image is converted into a vector, and then it's kind of converted back to an image. While remember the cat image, where when it was classifying the cat for a classification, it just needed that vector at the very end to determine, is it a cat or is it not? To go beyond that, to be able to then go on a pixel level classification, it only does that by converting the vector back to the image. ResNets, called residual networks, addresses what in statistics call vanishing gradient problem. I don't want to go too much into it, other than I just want to demonstrate that, in traditional neural networks like convolutional, you see from left to right, layer by layer, it's in sequence, right? Each layer feeds into the next layer and then eventually reaches the output if it's fully connected. For residual, it does that, but it also skips and based on how you arrange it and such, some hops away can also feed into other layers at the same time simultaneously. And so the way that it's done is, basically that's a characteristic of a ResNet. So I started to run out of time, and I just tried to, so I will confess, I know I in the agenda talked about explaining in detail, not in detail, but from an end-to-end perspective, how a workflow works. But for a couple of reasons, I wasn't able to really fit that in reasonably. One is because I realized that actually the workflow to kind of achieve, a deep learning kind of project for medical imaging is actually still very much in the research phase, which I actually was a little bit surprised with. I thought, the protocols were pretty kind of similar to what you see in data pipeline, the cloud today. But you know, I'm reading you know, variations of protocols on in literature, and it does range, and there's various things that you do, you know, but there's certain things that you absolutely do. I wish I could, maybe another time, that you do to ensure that you comply, you know, to HIPAA compliance and such as de-identification. And so for us, at least I can talk about what we sort of do here at Dentuit, is that we ensure that all our images, images that are going to be either be part of the test set, the training set, or the validation set, they are all de-identified. And I think you know, Dr. Price can, and the UMSOD personnel can speak to that as well. Is like, there's a very specific way to ensure that these images are de-identified of any patient information. Even having information about, let's say, the ID of the machine that generates the image is identifying information. But if it's, let's say, just a name of a machine that, you know, is generic and exists, you know, in various practices, then that's fine. That's not identifying because it exists in more than one place. But if it's traceable to some unique singular identifying information, then that is a red flag in terms of compliance. Okay, so going back to notable breakthroughs. In 2017, November, it was notable because I would say it was around that time, I believe, when the NIH did an unprecedented release of public data sets. And I mentioned that because that kind of comes back to the whole theme and the importance of data, and how that does, in fact, really help advance certain things in this particular field. And so in this respect, as soon as the, you know, NIH kind of released a data set like that, Stanford took those images and were able to kind of perform some kind of you know, computer vision kind of analysis on and created a net, and claimed, you know, things beyond, I believe, what they should have claimed, and it was controversial in many ways, including the notorious Andrew is a, I think he's, I don't know if he's still a faculty member at Stanford, but he's one of the earlier kind of um, he's sort of the face of deep learning, at least in the earlier stages. And he had a tweet saying, should radiologists be worried about their jobs? Breaking news, we now can diagnose pneumonia from et cetera, et cetera. Like I said from the very beginning, my personal stance, and this is not a place for me to kind of go on my kind of soapbox here, but I just don't see how that's possible right now with what we are able to do. And I think we would be doing the diagnosis a disservice, because I do believe it's just such a complex thing that, whether, I'm not a doctor, I'm not a dentist, but you know, when I think about how a diagnosis is made, it's so much more than just a pattern detection in an image. We just hope that we can provide a very reliable detection system that covers that base, so that then, you know, the dentist or the doctor can ensure that the diagnosis is being made in a reliable, consistent way, adding on other information. They're pulling in all sorts of information, you know, about the patient history, etc. Something that we do not go into because of various compliance or regulatory issues, but also just the complexity of it. In the future, maybe, but it all has to come together, both regulatory wise and also, you know, technique wise, or, you know, the computing is there, but the data access and the data availability in the medical space or the dental space, what have you, is still very much a problem. One of the problems, I will say, while I'm on this, that we try to somehow find ways to reconcile or deal with, is that medical data is notoriously difficult to deal with. You know, these medical images come from various hospitals. Each hospital has their own set of machines that have their own formats that kind of format their images in their own ways. And you can only imagine then because like the easiest kind of convolutional neural network implementation you can do is uniform sized images that you add in as an input, and you have very specific labels, and it's a very, you know, things that you see in an NVIDIA course, right? Let's classify this X-ray as either a chest X-ray or a hand X-ray, and they're all uniform size and no abnormalities or aberrations. That is far from reality in terms of what you know, we deal with in terms of data, and I'll go into that a little bit. The other kind of breakthrough I guess I want to cover, there's others. I just didn't have enough time nor the bandwidth outside of my work, so I do slightly apologize. But this was one of the more recent ones that came out. It came out in Nature, their paper, kind of providing what they called an international evaluation system, AI evaluation system for breast cancer, uh, for detecting breast cancer. And so I mentioned this because they it was notable, the study, specifically because of, if you look at the diagram on the right, the development of their AI system, they they utilize this idea of, well, can we generalize across countries? Can we use just the data sets from, let's say, Europe, and then the data sets from the US, separate them and then train them separately, and then see if we can then be able to, let's say, have an algorithm trained on UK, also then trained on US, such that any particular image that then gets analyzed can be it can perform and detect. And so that's one of the other things that we here at Dentuit, but any imaging kind of AI kind of sort of is always looking to kind of make sure that that's in place, is that as much as a pain it is to kind of understand that the realities is that the images are formatted in so many different ways, and it makes maybe the computer scientists' lives harder. At the same time, to have a very performant algorithm, you want it to be able to generalize to almost any formatted image for that particular domain. That means I want images from not only just this scanner, but I want it from that scanner, from that country, formatted in that way, and then have that algorithm also learn on that and be able to kind of get a diversity of things such that it avoids as much, let's say, algorithmic bias or overfitting that you kind of hear or read about in the news as much as possible. Because
Dan, let me just give you a time check. Up to 10 minutes.
okay, thank you, Seth. So that's one of the kind of use cases. I'm almost done. So I'll round it out with challenges here. And I talked at length about a few of them. And then one of the many challenges, of course, is in the medical space, especially, is limited data sets, for various reasons, all combined. One being the privacy and legal frameworks, and then really, and this is like the most obvious to understand, is that not anyone can just label these images. That's partially the beauty and the value that we are getting out of this kind of rare partnership with the dental school, is that we have now this kind of avenue of not only getting new images or adding to the data set, but having qualified labelers, experts, kind of labeling with their expertise on a set of images that we can have with multiple experts, such that then we can create that consensus and ultimately arrive at these graphical annotations representing that group of panelists, like I kind of mentioned at the very beginning. That annotation truly representing a consensus opinion, a second opinion from a group of really kind of highly qualified experts. That's the goal. That's what we want to get. And to get there, it obviously is not easy. It's costly and specialized, but the partnerships like this, it's a start. It's a start. So there are also workarounds with, let's say, limited in terms of like sparse or what they call low data regime. And one, I just want to go over just one out of the others. UNet obviously is there as one way to kind of handle sparse data sets. But data augmentation is nothing more than literally creating a new image by simply, let's say, flipping the image. The way that convolution works, it's directional, right? So it goes from one pixel on the very upper left, and it uses a filter slash kernel. There's subtle difference, but basically it goes from left to right all the way down, and it does an element-wise multiplication and addition. That's convolution. By simply flipping it, yes, at the end of the day, it's the same image, but it's ultimately a new image in terms of its operation, computational operation. So there's little clever things that you can do to increase, let's say, the size of your data set. And I did that on a very small scale with, let's say, 100 X-rays. And then I kind of expanded that by doing various translations of the images, whether, it's kind of shifting a little bit to the right or left without, altering the label and without adding noise. Because the thing, there's other techniques that you don't want to do that exist in computer vision. In terms of medical field, right? You don't want to be having an algorithm learning something that doesn't really exist in a prior knowledge such that it starts kind of detecting certain things that just it's it doesn't exist basically. And so we're talking about detection of tumor and cancer, and so we want to be very, very kind of evidence based with that in terms of learning. And then I guess I think this is this is really the only other slide that I have really, is another kind of example of just it's not an easy kind of task, as and so most recently I do want to kind of mention the importance of real world performance. Is that a lot of times these algorithms that are even deployed in a laboratory kind of environment, very controlled and such. But when we talk about adding users interaction and such, and how that can that it may not even have to do anything with the algorithm itself in terms of performance or accuracy, but just how people use it as a platform. And that's what the story was really about, was the medical AI in the real world. The UI UX of it was terrible, and it really didn't even want it really overshadowed the potential of the detection algorithm itself. And then IBM Watson for AI. I think we all know they're laying off people in that sector. It's been a fail really in one sentence, because they were trying to apply an algorithm that was designed for business kind of use cases into then applying that and hopefully generalizing that to healthcare scenarios. And they realized that they're not really the same thing, and that healthcare information data is just a lot more complex, and therefore it just didn't work that way. Other noteworthy challenges: standards. DICOM, I think, is one kind of avenue towards kind of standardizing into one image. It's the standard, I think, in medical imaging as well as dental. Algorithm bias, like I referenced, and then the unexplainable, the explainability of black box models, which I think will get better over time. And so obviously I know that there's presentations on this, even overviews and intros, that do a much better job than me. And so I made it a point to have this slide of a list of links that I thought was really good for anybody from any technical level to understand, especially the JAMA's machine learning for medical image analysis video, how it works. It's a YouTube video, very short, but it does an excellent job in demonstrating how exactly a filter kind of moves across an image and basically extracts and learns features in that way through, of course, the convolution and pooling, but they explain that in a much more intuitive way. So I highly recommend that. I recommend that. The Udacity virtual conference on AI for healthcare happened fairly recently, about a few weeks ago. And so I think this was a good example of just watching the recordings and them go over pretty well over the recent and current kind of issues and challenges that exist, not only in medical imaging, but AI for healthcare in general. And that is.
Dan, you're gonna provide a copy of your slides so that people can follow those links.
Oh yeah, sure, absolutely. I can give the PDF to you, and you can.
Okay,
I don't know the best way to do it.
You provide it to me, and I'll post it to the meetup site.
Okay, thank you, appreciate that. So I tentatively say Q&A because, again, John said that he will be more than happy to address the more technical or questions I don't feel comfortable answering, and he'll get back to you. Maybe I can add that along with the PDF that I'll give Seth. But the more general things, I can certainly do my best to answer. But yeah.
Well, I'm gonna ask you a question myself. Sure. And for other people who want to ask questions, you can put them in the Q&A or raise your hand. But as I said before we got started, I want to try to do some networking after we're done with Dan, after he's finished the Q&A. So I'm going to start changing people to panelists so that they'll be able to participate in just an open exchange. You've probably all done Zoom meetings after we're done. But let me ask you a question as I do that. So Dan, as you know, I run an AI roundtable for the Maryland Technology Development Corporation, TEDCO, and we have a couple of participants who are in the medical field, and one of them in particular, Vineet Sachdev, for instance, is using imaging to look at colonoscopy analysis. And another one, Jim Fackler, who's a physician, is looking at sepsis, at blood infections. And Jim has made the point in particular that if you train your models on data that shows only pathologies, in other words, you've already screened them and said, hey, this person is sick in some way, then you're going to get a model that is not applicable in a normal situation where there's a low proportion of pathologies. So yeah, sure, if you go into the dentist's office, oh, I'm making this up, maybe 8% of people who visit the dentist actually have a cavity. But if you train your dental models where 98% of the people have cavities, you're going to get models that are inapplicable in real life. Can you comment on this, on the training data?
Yeah, so a little bit, I guess. We're still in the process of learning how to kind of gather, at least right now with the medical space and the dental space, like any data is better than no data at all. And there's ways to kind of to unsupervised learning and various kind of things, kind of work around the lack of label data, quality label data, or the label data that you're kind of referencing. Um, I I I I think there's just various ways to kind of acquire and somehow do it, but I don't know. For now, yeah, I don't. For now, I try to kind of uh, imagine that we want a certain ratio for a certain. So let's say a certain X-ray is used for a certain kind of lesion. In this case, for us, there's a certain kind of ratio, but we don't only still just take those X-rays. There's other X-rays that the dentists take to kind of maybe see other lesions, but yeah. So I don't know other than just I think right now we try to just uh, not be too we try not to like control or influence like the data set in terms of you know we only want to get just x-rays that have a particular lesion or what have you, but rather get as distributed of a data set as possible. So that may kind of lead in kind of just come back to my kind of impression or my stance on this idea that sure, having more data will allow for better distribution and more kind of opportunities to generalize. And
Yeah,
so
something to keep,
yeah, go ahead.
yeah, something to keep in mind. Let's take another question. Actually, George Soto, you had two that you put in the Q&A. You're able to speak if you want to unmute yourself and go ask your questions live. George?
Sure, yeah. Hi, Dan.
Yes, sir.
My question is,
Also, if you wish.
yeah, my question is, apart from imaging, is deep learning and AI used in your applications with other data types like structured data or text or audio or other data?
No, right now it's only just image and a very specific ratio of the type of x-ray image for a certain, like I said, lesion detection. The text, of course, the possibilities are there, right? The patient's metadata. But I think John and I, we kind of decided early on, at least to start, that let's be very good at this particular mini task that is a small part, but an important part of the overall kind of workflow or the diagnostic kind of protocol that a dentist may have for a patient, and be very good at that so that we cover that base. And so if that means being very good at detecting something in an image, then I don't think we need additional text to achieve that particular task. But like I said, to make that jump from detection to diagnosis, yes, absolutely. In some world or some kind of situation where that's easy to do, or the barrier to that is easier to do, then sure. But that will then maybe allow for broader applications. But right now, for example, if I wanted to get text-based information for a particular patient, to be able to apply the protocol to de-identify that and do that, it's more work than we want to kind of assume in terms of the value return.
George, you have another question? Someone had a question about the classification prediction applications. Does that person, it's listed as anonymous, does that person want to unmute and ask that directly? No, okay, well, go ahead. Do we have a questioner? No. So
I can ask a question, Seth, if no one else is going to ask. This is Jeff Wright. Yeah, hi, Dan. Enjoyed the presentation. So I'm the primary investigator at the dental school, the radiologist. So I'd like to address the question about how did we select our images and the idea or the concept of how much disease was present and that topic. So what we did was go back through our database in our PAC system at the school, beginning in July of 2016 and went through the end of March 2020 and selected every sixth image. So that in each, well, not to get into the specifics so much, but in every category of image that we're looking at. So we did a very random kind of approach. So then you get down to what's the rate of disease on dental radiographs. And in the population in Baltimore, it might vary a little bit according to the, or as compared to the rate of disease in the US population, but so does every other dental school. So it's a systematic bias, probably, because you could say that people with a little more dental disease go to dental schools to request treatment so they can save a little money because they need a lot of treatment. So I think that could be accounted for somehow when you look at the, you know, the end result. But at any rate, that's how we approached it. So it's a completely random kind of image selection. It's not like somebody cherry picked it all. So anyway, just a comment.
Yeah, thank you, Dr. Price. Appreciate that. And I know you also applied the de-identification protocol to ensure all that. And
yeah.
So,
And it was,
thank you.
I can't remember the name of the program right now. It's out of the University of Washington. I can't. Somebody on the some of the other participants may remember it right now, but I can't remember the exact program. But you run it, and it'll chew through thousands of images in a matter of, well, I don't know. It was a very short period of time, and in a matter of hours, and ran through all the images and de-identified everything. Right. Yeah.
Thank you.
All right, going back to that question that was, thank you, Dr. Price. I will just further remark that understanding the potential for bias and looking for the possible sources is a key step, even just being aware. Going back to a question from Q&A about deep learning classification prediction applications in dental science, are there others you care to address there?
Well, I'm sure Dr. Price again can kind of think of all. I know they have their own projects as well beyond just our partnership. They're looking at one of the main kind of problems I think that is interesting to me, that is beyond the scope of our partnership for now. But I think Dr. Price is pursuing this. Is what do we consider, and this is applicable to medical imaging as well. What is ground truth? Maybe when we talk about, let's say, the medical space and a specific tumor, let's say, then you do the biopsy to get the golden truth. But between that ground truth and the golden truth, that spectrum of what is sufficient and what is not, is it just a matter of an algorithm that gets to a certain level of accuracy and performance that is sufficient, such that, yeah, we may never have trained on the golden truth, but maybe our ground truth was good enough such that we didn't need to do a biopsy? Because, for example, with the dental space, imagine what a biopsy on a caries would be. That would literally be going to the individual's tooth and hoping that the tooth would even be extractable and such. And I'll, if Dr. Price, if you take the liberty to kind of add to that, because I know that is something.
Yeah, sure. I'll be glad to comment, Dan. Yeah. So you can't do a biopsy on a tooth in a person. So you have two choices. You can take the tooth out and do histology, a biopsy, if you will. And then, you can take the tooth out and do some other types of radiology, like micro CT and things like that. So there's other types of studies, and Dan and I have talked a little bit about it. And so we're developing what we call a caries database study. And I don't want to get overly involved with details. So, but we are running our own little separate caries database study, looking at not only routine dental imaging, as you all would know about it, but it's typical images that a regular dentist would be taking, but also new dental imaging that it hasn't been FDA approved yet. Stationary intraoral tomography, which would be like 3D breast mammography. There's, well, as I mentioned, micro CT. There's MRI, which will be at the end of the study, and cone beam CT, dental cone beam CT, which is the first cousin of medical CT, and so on. And so those are, and of course we'll do regular bite wing imaging as well. So there are lots of other imaging modalities. So the gold standard historically has been histology, where you section a tooth and look at and evaluate the depth of demineralization and caries. But an excellent surrogate for that is micro CT, which is what we're likely to do. But we'll also take a small subset of that and do some histology, some sectioning of the teeth, and see how well that compares to all these other imaging techniques. And then,
and that reminds me, the difference in computer vision approach is that the difference between, the X-rays that we're looking at on our side is just simply 2D. But there's a whole nother approach with a set of nets that you want to be looking at. So you want to be very kind of cognizant of the type of not only kind of objective that you're trying to achieve, but with the advent of imaging, like as it advances into like 3D imaging, there's a whole kind of other kind of sector of computer vision that focuses on those kind of things, from medical imaging to dental imaging as well.
Right. So, but anyway, but this kind of stuff is, we will be really significantly, and Dan and I have talked about it, hampered by the pandemic, which interrupts our whole scheme of things on this other study, not directly related to the Dentuit partnership. So anyway, enough said, I think. So yeah, there's a lot of other things going on.
Are there any other comments or questions from people who are attending for Dan or for Dr. Price? You can just unmute yourself and go ahead. Any others? Okay, that's fine. So thanks very much for participating, for presenting, Dan, and for Dr. Price for jumping in there as well. It sounds like really interesting work. I wish you good luck at bringing this office. Ankit, did you want to say something?
Yeah, sorry, I think I was accidentally mute or something. I just had one question really quick about the object of screening for this particular service really is that there's something about right now the object is replication, right? About detecting and replication in which an expert would be able to detect an image, and that's why there's expert labelers who are doing that hard, gritty work of doing that. In other areas of image classification that have been promoted in recent, I guess, months and years, where we're talking about tumor analysis or recognition of tumors that is at a level of type 1 and type 2 error that is an order of magnitude less than expert practitioners. Is the end goal here to be an improvement alongside as a screening tool, or as like a replication of expert analysis? Because it kind of goes to Seth's point about like frequency or incidents, about kind of being a check against that human bias and error that we just always is innate to us, of pattern recognition and going beyond that. So I guess my question is really about, at what point would you be comfortable with pushing beyond a replication ordered, labeling ordered system, and trying to push like beyond into a realm where the detection is done um, you know, at a point that is greater than any collection of experts doing it themselves.
Right. So for me, I mean, you would have to start somewhere. And so for me, you know, our approach from a certain kind of point was to just to be very good at the replication part, to be very robust, because it is, and a lot of it you have to start then thinking of it outside of the computer vision technical components of it, of what's possible or not, but just also ask the question of what is the end user willing to do, or what does end user need? Because, for example, there's, you know, a story, you know, there's not stories, but like situations with the COVID and the radiographic screening where they believe that, sure, I'm sure there's some good technology that helps screen COVID right off, you know, right off the bat from the ER, but, you know, like they also don't, there's pushback because there's also existing, you know, non, you know, deep learning or AI based technologies that have already existed that may already kind of be potentially better at, not better at, but like it can do the job more or less. And so I think the point I'm trying to make is it comes down to the objective of what not only you're trying to achieve as a computer scientist, but really the objective in terms of the problem at hand. And its problem at hand can vary, and it ultimately comes down to the end user, for us anyways, because it is the dentist at the end of the day that will be making that business decision to either purchase it or not. So we try to kind of strike a fine balance between kind of what is possible in terms of technology versus what makes sense to the end user. Because what may make sense in terms of just being, you know, in terms of computer science can almost be limitless if you want to kind of be ambitious about it. But in terms of what is even meaningful in terms of value returned from that, we cannot automatically assume that that is in fact what they wanted or what they want. So it comes back to kind of this notion of making sure and checking in and ultimately kind of working with the right kind of people to ensure that this is an interdisciplinary approach to a solution.
Ankit, do you want to follow up? If you do, just unmute yourself.
Oh, yeah, thanks. I'm sorry about the feedback. The only other question I had was, and I agree with you, it's like kind of a big scope kind of issue regarding going to that next step. But within the current framework you have, you mentioned about how the diversity of images and how each set of images, depending on what clinic you're getting that information from, is done on a different machine or done in a slightly different way. And it seemed like a hindrance the way you had mentioned it. Is it in, you know, could it also be seen as a benefit in that you're receiving this large diversity of images that are marking the same thing, just in a slightly different manner?
100%. Actually, I think I referenced that later on when I kind of touched upon algorithmic bias. I don't know if there's any other way to avoid bias other than trying to, I guess that's the kind of intervention that one would want to do in terms of aggregating their data set, is ironically just ensuring that it's as, I guess, difficult as possible. It ultimately comes down to, you know, a balance again. I know no one wants to hear the "it depends" kind of answer, but, you know, ultimately we have to still all take that and somehow, you know, format that as input and compute it, right? So it's great if we, you know, ideally we have like, and I think there are algorithms that are looking to address that as well, that it can take, you know, different size images. I know that they exist, and then maybe things beyond that to kind of account for the differences. But yeah, if I had to choose one or the other, of course I would go with the data set with the distribution of in its variety. And almost in a way, it's almost impossible to avoid and have this uniform approach. And if anything, it also lends its way into possibly generalizing to other things, whether it's detection of other pathologies or what have you. I don't know if you heard of Path AI. Their approach, apparently one of their approaches was that they don't care much about the specificity, but the generalizability of their algorithm. And so in terms of their pathology kind of use case, they would much rather have just large volumes of all kinds of pathology-based images, such that maybe they're not, well labeled all the time, but it allows their algorithm, what they say anyways, to be able to generalize to many kinds of things to sufficient accuracy, to sufficient performance.
Okay, why don't we say thanks to Dan and give anyone else who's on the line still. We have a total of 19 people. Anyone else is on the line right now who wants to just say something for a moment, just to introduce yourself and something that you're working on. And I'll repeat, by the way, the possibility of giving a meetup talk yourself. And I'm also going to flash up a poll right now about the timing of future programs, just to find out what you all would prefer, if you care to express a preference. So anyone else want to say anything, introduce yourself very briefly, say anything about what you're working on, if you have any company, things like that. Please go ahead. Any takers? Just jump right. And it looks like you might want to.
Hello. Hello, can you hear me?
Yes.
Yes.
Hello, my name is Martin. I'm greetings from Latin America. I am now starting my PhD in generation of medical reports from images using deep neural networks. I just want to thank you, Dan, for your talk. It was really clear, and the application side of this technology is certainly very interesting. And I just want you to know to take into consideration that maybe you could benefit from applying an attention mechanism, or you could track recent developments in attention mechanisms in neural networks, for example, when generating text from images. That is what I'm studying, and it is certainly very interesting to see how it works out with medical science in these regards.
Yeah, we actually have, without giving away too much, we're actually kind of looking into that and exploring this notion of perception and attention, and learning that, whether it's at the same time or what have you, in the way that you kind of structure your architecture to analyze it. We're looking into that. So I'm glad that you brought that up, actually.
Any other comments or self-introductions? Well, if not, we'll call it a day. So as I have indicated previously, we're going to try to do these programs maybe every month or 6 weeks. I'll thank once again Amazon Web Services, Maryland Recruiting, for their support, which helps cover the costs of doing this. We will have a program in a couple of weeks, I haven't set a date yet, that will be an online version of the Maryland AI Roundtable that I mentioned earlier, that I facilitate for TEDCO, the Maryland Technology Development Corporation. Everyone will be welcome to participate in that as an attendee, and then after round, we'll see how the discussions go, and we'll enable people to join in. If you are interested in the roundtable, also just send me a note telling me a little bit about what you do if you want to become potentially a regular member, and I can tell you a little bit more about how the roundtable operates. So once again, thank you very much, Dan, for presenting to me today. If anyone would like to give a talk in the future, let me know, and otherwise we'll see you next time.
And I'll give the PDF to Seth, so look out for that.
Yeah, we'll get it posted, and I will also post video of this session. Thanks, everyone.
Yep.